The slice type. Another data type that does not have ownership is the slice. Slices let you reference a contiguous sequence of elements in a collection rather than the whole collection. Here's a small programming problem. Write a function that takes a string and returns the first word it finds in that string. If the function doesn't find a space in the string, the whole string must be one word, so the entire string should be returned. Let's think about the signature of this function. Function, first word, takes s of type reference to string, resulting in This function first word has reference to string as a parameter. We don't want ownership, so this is fine. But what should we return? We don't really have a way to talk about part of a string. However, we could return the index of the end of the word. Let's try that, as shown in listing 4.7. Function first word, parameter is s of type reference to a string, result usize. Let bytes equal s dot as bytes for I reference to item in bytes dot iter dot enumerate if item equals bytes type empty space return I s.len. Okay, because we need, here it is over here. I called it first jank because it's not going to work. Well, it's going to work, but they're going to say it's dumb. Because we need to go through the string element by element and check whether a value is a space, we'll convert our string to an array of bytes using the asBytes method. Okay, so string comes in at in the variable s, reference to string, and then we use the asBytes method to convert our reference to string to bytes. Sure. I wonder if bytes is like characters, because they do have the single quotes here. Next, we create an iterator over the array of bytes using the iter method. For so two looks like parameters for I, comma, reference to item in bytes dot iter dot enumerate. We'll discuss iterators, thank you, in more detail in chapter 13. For now, know that iter is a method that returns each element in a collection, and that enumerate wraps the result of iter and returns each element as part of a tuple instead. The first element of the tuple returned from enumerate is the index, and the second element is a reference to the element. This is a bit more convenient than calculating the index ourselves. Because the enumerate method returns a tuple, we can use patterns to destructure that tuple, just like everywhere else in Rust. So, in the for loop, we specify a pattern that has I for the index in the tuple and reference to item for the single byte in the tuple. Because we get a reference to the element from .iter.enumerate, we use a reference in the pattern. Okay? I don't understand what I just read. But when I listen to it a bunch of times, I'll start to understand it. Inside the for loop, we search for the byte that represents the space by using the byte literal syntax. If we find a space, we return the position. Otherwise, we return the length of the string by using s.len. We now have a way to find out the index of the string, the index of the end of the first word in the string, but there's a problem. We're returning a usize on its own, but it's only a meaningful number in the context of the reference to string. In other words, because it's a separate value from the string, there's no guarantee that it will still be valid in the future. Consider the program listing in 4.8 that uses the first word function from listing 4.7. So that is this. Let mutable s equal string from hello world. Let word equal first word. Let word equal reference to string first worded, I guess. And then we can say s.clear. This empties the string, making it equal to nothing, empty string. Word still has the value 5 here, but there's no more string that we could meaningfully use the value 5 with. Word is now totally invalid. So, what they're saying is, cargo, Ron, it runs, it compiles, but we just whacked string, we just whacked our string, hello world. All we have in Word is the number 5. We can't go back and get other things from the string because it's gone. Or rather, it has been mutated into nothing. This program compiles without any errors and would do so if we used Word after calling sclear. Yeah, right there. Because Word isn't connected to the state of s at all, Word still contains the value 5. We could use the value 5 with the variable s to try to extract the first word out, but this would be a bug because the contents of s have changed since we saved 5 in Word. Having to worry about the index in Word getting out of sync with the data in s is tedious and error-prone. Managing these indices is even more brittle if we write a second word function. Its signature would have to look like this. Function second word takes reference to a string called s and results in a tuple, I guess, usize. Now we're tracking a starting and an ending index, and we have even more values that were calculated from data in a particular state but aren't tied to that state at all. We now have 3 unrelated variables floating around that need to be kept in sync. Luckily, Rust has a solution to this problem: string slices. A string slice is a reference to part of a string, and it looks like this. Let s equal string from hello world. Let hello equal a reference to s, and then square brackets, inside that 0.5. Let world equal reference to s, square brackets, 6.11. This is similar to taking a reference to the whole string, but with the extra square bracket 0.5 bit. Rather than a reference to the entire string, it's a reference to a portion of the string. We can create slices using a range within brackets by specifying starting index ... ending index, where starting index is the first position in the slice, and ending index is one more than the last position in the slice. I'm sure there's a very good reason for that. Internally, the slice data structure stores the starting position and the length of the slice, which corresponds to ending index minus starting index. So in the case of let world equal reference to S, what's the word I want? Range. Where's that? They use the word range, right? Range, yeah. Create slices using a range. So let world equal reference to string range 6 to 11. World would be a slice that contains a pointer to the 7th byte of string S with a length value of 5. Okay. So here's a diagram. So S has a length of 11 and a capacity of 11. And we've got a value, a pointer value that points to the heap at index 0, which is where the value H is. And that the range for the word hello goes, well, let's see. Hello occupies indices 0, 1, 2, 3, 4. Index 5 contains a space, and then world picks up at index 6. And it takes 6, 7, 8, 9, 10. So I guess, so the values here for length and capacity are 1 indexed. They count starting at 1, whereas the value, the actual indices are 0 referenced, 0 indexed. So if we want hello, we go from 0 to 5. So HELLO space, except not really, because because in the range we're giving it the end of the range, the ending index is the index value plus 1. The index value we actually want to stop at plus 1. So, or not index value, the index. Yeah. Index plus 1 is the end. Whew. So what did it say that made me go hum? In the case of, so in the case of let world equal string slice starting index 6 through ending index 11, world would be a slice that contains a pointer to the 7th byte of S. The 7th byte of S, because this is the first byte of S. The 2nd, 3rd, 4th, 5th, 6th, 7th. The 7th byte of S, the length value of 5. 1, 2, 3, 4, 5. Yep. I guess that's just going to have to take some getting used to. I mean, it makes sense. Is 0 indexing just strange? No, because we need 0 indexing for binary, right? That's where it came from. That's why we use it. So with Rust's ... range syntax, If you want to start at the first index, 0, you can drop the value before the two periods. In other words, these are equal. So we have let slice equal reference to s 0.2 from hello, which would give us, so this is 0. Wait, 0.2. Okay, so this number is one more than what we're asking for. One more than what we really want. Right? So that gives us just the h, I think. And then let slice equal reference to s dot 2. Okay. Excuse me. Should be the same. I didn't say. Run. By the same token, if your slice includes the last byte of the string, you can drop the trailing number. That means these are equal. So the string from hello, if we take the range of 3 to len, what? Okay, yeah. So we have a variable string, which is the string. It's just a string. And then we're getting len of s. So we have len. So len is the number that is equal to however long the string is, which in this case would be what? 1, 2, 3, 4, 5. Yeah. They did. Why did they do that? Why couldn't they just give me a 5 there? Making me think. So we have from 0 to len, it's the whole word. So let slice equal reference to s, and then range with no beginning or ending index named. That'll give us the whole thing. So it's like full range, the dot dot. Note, string slice range indices must occur at valid UTF-8 character boundaries. If you attempt to create a string slice in the middle of a multi-byte character, your program will exit with an error. For the purposes of introducing string slices, we are assuming ASCII only in this section. A more thorough discussion of UTF-8 handling is in the Storing UTF-8 Encoded Text with Strings section of Chapter 8. With all this information in mind, let's rewrite first word to return a slice. The type that signifies string slice is written as reference to stir. Okay, so function first word takes in a reference to a string and returns a reference to stir. Let bytes equal s as bytes. Do I have to say reference to stir? Do we ever use stir without a reference? I haven't seen it. So let bytes equal s as bytes. For I and item, for I, comma, reference to item in bytes, dot iter dot enumerate. If item is equals, I should say equals there because there's two of them. Haha. I will say equal if there's one. I will say equals. This could be B. This is just a, what do you call it? Linking verb. It's a conjugator. No, it's a, what is it? It's the copula. That's the copula. And then this is a question and this is a statement. Kinda. Okay, here we go. So if item equals bytes, a byte of empty space byte, return reference to s with this range 0 to I. So if I is a space, then we want to return reference to the string up to that space. but not the space. That is why this works. Now, this is what I was thinking. Why I'm sure it makes sense. I'm sure it has something to do with spaces. Why we want the ending index to be one bigger than the index in the heap for, we'll say, the character O is what we're looking for, something like that. So we can find the one that's this and say, okay, so it's this number, which is actually one more than that. I don't know if that was the reason for it, but it sure does help. So, returning reference to S, which is the range that goes from the beginning, so we could leave that out. That doesn't need to be there. All the way through until you find I, which is a space, and then back up one. That's what I want. And down here, we're just saying the whole range, which is the whole range of the slice, which is a reference to S. Huh. Okay. We get the index for the end of the word in the same way we did. We get the index for the end of the word in the same way we did in listing 4.7 by looking for the first occurrence of a space. When we find a space, we return a string slice using the start of the string and the index of the space as the starting and ending indices. Now, when we call first word, we get back a single value that is tied to the underlying data. The value is made up of a reference to the starting point of the slice and the number of elements in the slice. Returning a slice would also work for a second word function. Yeah, I guess you'd have to find two spaces. Okay, we now have a straightforward API that's much harder to mess up because the compiler will ensure the references into the string remain valid. Remember the bug in the program listing in 4.8 when we got the index to the end of the first word but then cleared the string so our index was invalid? That code was logically incorrect, but it didn't show any immediate errors. The problems would show up later if we kept trying to use the first word index with an emptied string. Slices make this bug impossible and let us know we have a problem with our code much sooner. Using the slice version of first word will throw a compile time error. Let's try it. So I have, it's called first slice. I will go to my main function and we're good. Hey, looky there. It already tells me that sclear is yeah. Oh, that's just telling me what this does. Okay. Hey, I really hate having to use my mouse to come get these. Do you happen to know of if you're listening to this, is anyone out there? If there is an extension or a setting I can use where I don't have to hover the mouse, and I don't know about it yet, if you could tell me, I'd appreciate it. So we have, yes, this compile time error we expected. Immutable borrow occurs here, mutable borrow occurs here, and we know that is a no-no. And then immutable borrow later used here. Well, yeah. So the compiler error. Recall from the borrowing rules that if we have an immutable reference to something, we cannot also take a mutable reference. Because clear needs to truncate the string, it tries to take a mutable reference, which fails. Not only has Rust made our API easier to use, but it has also eliminated an entire class of errors at compile time. So, why does it work for this version? It's taking in an immutable reference to string. Well, string is mutable. Okay, but it's taking in an immutable reference. And it's outputting a usize. It's resulting in a usize, which is not the string. It's not a reference to the string anymore. It's just it's totally different. So that means when we so we have a reference comes in here, right? But then this function, no, it's not a function, this statement, no, there's a function there, firstjank. So firstjank runs and then finishes with referring to the string, which I guess it doesn't have to finish because no one else cares about referencing the string. However, the next one, what I'm calling first slice, it takes a reference to the string the same way, but it outputs a reference to stir. It outputs a string slice. So that is still, it's still referring to the original S. What happens if we just take out this S clear? I mean, we'll let print, what will word even be? Word will be our slice, which is going to be the first word. Yeah, because we're going from 0 to the I. We're talking about what usize? What usize are we talking about? That's a usize? That's a U8. I guess, because, oh, we took it to bytes. Okay, let's try it. Oh, that's big. Cargo run. Hello. There we are. Help! Remove this mutt. Really? Well, if we remove that mutt, does that mean we can clear the string? No, we can't clear the string if we take away the mutt, of course. We just don't need it. Okay. Oh. Oh, there we go. 1, 2. There we go. Am I still recording? Yes, I am. Okay. Hey, looks like I know what's going on because I got htop and this, but it's not really doing anything. Oh yeah, it is. Look at that simple screen recorder. It's using it. Ho! I knew there was I do know what's going on. Smart guy. Where was I? String slices. String literals are slices. I don't know if you knew that, but they are. Knowing that you can take slices of literals and string values leads us to one more improvement on the first word, and that's its signature. Function, first word, takes in a string, puts out a string slice, I think. A more experienced Rustation would write the signature shown in listing 4.9 instead, because it allows us to use the same function on both string values and stir values. function first words takes in a stir, puts out a stir. If we have a string slice, we can pass that directly. If we have a string, we can pass a slice of the entire string. Defining a function to take a string slice instead of a reference to string makes our API more general and useful without losing any functionality. Let my string from hello, yes, let word equal, so let word equal first word for, oh, wait a minute now. Yeah, so all we have to do is, if we change the parameter here to a stir, and then coming into it, instead of, where am I on? Yeah, let's get rid of that. Right, so this is what? A ref, we wanna, okay, reference to S. What in the world? Why I gotta change it? S. That, the whole thing. That looks suspicious. Like it's a, okay, well anyway, so this is a string slice, and it's telling us it doesn't want to be mutable anymore. Well, it'll be alright. Okay, then let my string literal equal hello world. What? Hold on. So got let my string equal string from hello world. First word, or in my case I've got first slice. It works on slices of strings. So now we have let word equal first slice with an argument reference to my string, but with the range of the whole thing, which means this is a string slice of the whole string. So whenever you see the reference, it's not a reference to a string slice per se, because a string slice is always a reference, I think. Alright, and then println word. So that should just give us the whole thing, right? Hello world, or don't you think? Or what are we looking for? Yeah, I think so. Give us the whole hello world. Now, let my string literal equal hello world, which is already a string slice. I think we get that down here. Okay, I'm getting ahead. So let word equal first slice. Oh yeah, the first slice function. Duh. So that means it's going to be hello. Yeah. Yeah, so the word will be hello. And then down here we have hello world. Ew. Just the string literal, my string literal, hello world. Let word equal first slice from a string slice of hello world, which is already a string literal. String, okay, a slice that is the whole thing. Full range slice. Goes in, comes out no problem. As hello. Now let word equal first slice my string literal. Yeah, so we're not even gonna try to say turn this into a string slice because it already is one. Println word. So this should just give us hello, hello. How many times? 1, 2, 3. 3 hellos. So, I'm gonna run. Hello, hello, hello. Wonderful. Other slices. String slices, as you might imagine, are specific to strings, but there's a more general slice type too. Consider this array. Let A equal 1, 2, 3, 4, 5. That looks a whole lot like slice syntax. No, it doesn't. I mean, it's got the... Well, anyway. It's got square brackets. That's all I meant. That's all I noticed square brackets. I get excited. Just as we might want to refer to a part of a string, we might want to, we're gonna want to refer to part of an array. We would do so like this. Let A equal 1, 2, 3, 4, 5. Let a slice equal array slice ranging from 1 to 3. Whoa. Now that I'm wondering about, because is this 1? This is 0? I think we talked about arrays in a different chapter, and I have forgotten. Okay. This slice has the type reference to I32. Whoa. Slice of an I32? Is that what that is? Okay, it works. Reference to an I32 array? I don't know what that means. It works the same way as string slices do, by storing a reference to the first element and a length. You will use this kind of slice for all sorts of other collections. We will discuss these collections in detail when we talk about vectors in Chapter 8. So that's the end of Chapter 4. It is. Hey, it's great. Summary. The concepts of ownership, borrowing, and slices ensure memory safety in Rust programs at compile time. The Rust language gives you control over your memory usage in the same way as other systems programming languages. But having the owner of data automatically clean up that data when the owner goes out of scope means you don't have to write and debug extra code to get this control. Ownership affects how lots of other parts of Rust work. So we'll talk about these concepts further throughout the rest of the book. Let's move on to Chapter 5 and look at grouping pieces of data together in a struct. I just said data. I've noticed I say data every time, or I have been. I saw something probably on YouTube that said that like some people said data. You know, earlier in the 20th century, some people said data, but most people said data. Until Star Trek: The Next Generation. Character named Data, and so that pronunciation gained prestige overnight.